So guys, in this video I will show you how to derive the first two kinematics equation. This is the only thing that is given, that the acceleration is constant. And we are going to use calculus to integrate this equation. Okay, so anytime you see variable a is not a variable, is a number. Okay, so the definition of acceleration is the derivative of the velocity versus time is a, and a is a constant. And over here I will put it with numbers. Let's pretend that the acceleration is 2 meters per second squared. 2 meters per second squared. So you multiply by dt. That's a thing that physicists do. And you now integrate over here from the initial to the final velocity. And over here you integrate from 0 to t. And this is just going to be v minus v naught, and this is going to be a t minus 0. So meaning that the velocity is the initial velocity plus at. This is the second kinematic equation. And let's assume that the acceleration is positive 2. And let's assume that the initial velocity is 1. And that is the first derivation. If this bothers you with numbers, we could use number 2. So the same thing, dv is 2 dt. And then you integrate from v naught to v, and integrate from 0 to t. And this is v minus v naught, because this is just constant function 1. And this is 2t minus 0. So v is v naught plus 2t. Let's say that the initial velocity is 1 meters per second. So v is 1 plus 2t. That is what I plot on the left over here. Okay, this is the second kinematic equation. Now we are going to get the first kinematic equation. You know that velocity is the derivative of position over time. So this is what we have on the left hand side, dx dt equals v naught plus at. Again, we multiply by dt. And do the same process. We integrate from initial position to final position. Sometimes I don't put f for final, I just put x, it is understood. And here you integrate from 0 to t. You integrate on both sides of the equation. So here is x minus x naught. The derivative of a constant is vt. And the derivative of at is 1/2 at squared. Remember, v naught is a constant, is the initial velocity, and a is constant because this is the case we are analyzing. And now, so this is the integral of v naught at. As you can see, it's a quadratic function. And now you evaluate at t and 0. So because this has t 0 and 0, so the right hand side just becomes this. And this is the first kinematic equation. And as you can see, it's a quadratic function of time. Let's assume that the initial velocity is positive 1 meter per second. So initially over here the velocity is 1 meters per second, and let's assume the acceleration is positive. So this is position versus time. And the initial velocity is 1 meter per second. Just use that like an example. And let's say the initial position is 5. Okay, we are going to do the same over here with numbers. So we have dx dt equals 1 plus 2t. And now we multiply by dt. And we are going to integrate this. Let's pretend the initial position is 5 meters to x, from 5 to x. And here we integrate from 0 to t. So over here we get x minus 5. And here we get the integral of 1 is t. The integral of 2t is t squared. And this is from 0 to t. So you get x minus 5 equals t plus t squared, or x equals 5 plus t squared. Which makes sense, because if I make the acceleration to be 2 meters per second squared, 1 a is just 1. See? This one over here. And the initial velocity, I made it to be 1. That's why you have a 1 over here. And the initial position is 5. So the initial position is 5 meters. The initial velocity is 1 meters per second. And the acceleration is 2 meters per second squared. So this is this particular case, but this is the general equation. So this is the two equations I derived by integrating a equals constant. So anytime you see this equation, the acceleration is constant. The acceleration is constant. In the second videos in this playlist, I will show you how to derive from 1 and 2 a third equation that is written like is this, and a fourth equation that is this. So these are the fourth kinematics equations. I show you the derivation of this. For example, the third does not have time, and the fourth does not have acceleration. The fourth is the most confusing one because it's motion with acceleration, but the acceleration is not in the equation. And people think this is a linear function, but it's not, because this v over here, this velocity over here, is number 2, and it's a function of time. It's a linear function of time. A linear function of time times t, it gives you a quadratic function. So this is quadratic in time, although it doesn't look like. Linear in time and quadratic in time. And this is a square root of the position. The velocity is a square root function of the position. Okay, so remember, acceleration is dv dt, the derivative of the velocity over time, and the velocity is the derivative of the position over time. And if you want, acceleration is the second derivative of the position over time. So from this equation in this video, I derive 1 and 2. In the second video, I show you how to get 3 and 4 from 1 and 2. And just as a summary, remember that all these are constants. Initial position, initial velocity, acceleration. The variables of the quantities that change in time are position later in time and velocity later in time. And what is the independent variable? In physics, the independent variable is time. So usually that is what goes on the horizontal axis. And here you can have position, velocity, etc. So constant initial position, initial velocity, and acceleration, variables, position, and velocity later in time. This not over here means at time 0. And the independent variable is time. So this is a summary of the calculus physics of the kinematics equation.